Greetings again from Washington, D.C., where we're all seriously sleep deprived, but I'm going to hope that I can make some sense. What we're going to do is we're going to look at chapters 5.1 and 5.2 from Strang about determinants. There are two videos, hour-long videos that he does. I think they're a little long-winded, and that's pretty arrogant of me to say so. I shouldn't say that. But I want to try to boil it down so that, and take a more traditional view of it. What he does is he starts with 2x2 matrices and talks about everything he possibly could about 2x2 matrices, and then just this kind of extends it to n by n matrices. And I wanted to take a little bit different approach, which is good because you can watch the other two videos, his two videos and this video, which is going to be shorter. I know you've heard of determinants before, determinants of a matrix. Somewhere in your past you have had to read a definition that referred to what the determinant of a 2x2 matrix was. And the definition was always, here's a 2x2 matrix, the determinant is a real number, it's this number times this number minus this times this. So it's AD minus BC. I know you've seen that somewhere. So you have been exposed to determinants in that way. And this is typical. Often in books, they'll just, here's the definition of a determinant, and they don't give you any motivation. We're going to have some motivation in this talk. You also, in Calc 3, you saw it as cross products. You were actually, remember the I, J, K, and then you had numbers down here, and you were getting, you had two vectors in R3, and you were getting its cross product. And you did it this way. You said I times the determinant of BECF minus, you had to have a minus, J times the determinant ADCF plus K times the determinant of ADBE. So in each case, you said, okay, it's this I times the determinant that's left of the matrix that's left when you cut out the column I is in and the row I is in, and then you just have BCEF. You cut out the column J is in and the row J is in, and you have ADCF left. You cut out the column and the row that K is in, and you have ABDE left. And remember, straight bars represent determinants. So this is not the matrix, but the determinant of the matrix is represented by the straight bars around the matrix. And then you took the determinant of this, as defined, the 2x2 determinant is BF minus CE, AF minus CD, AE minus BD, and then you multiplied, you could distribute the I and the negative J and the K, and you get that. Okay, I know you've done this somewhere in your past. You've done this. Oftentimes the cross product is just defined this way for convenience. So we know how to get the determinant of a 2x2 matrix, although we don't know why we want it, nor what it is, supposedly. How do we extend this to n by n matrices? So the way we extend it is by cofactor expansion. So here's a 4x4 matrix. And actually we do the same kind of thing that you did for the cross product with the IJK. We do a similar thing. This is how we, no matter how big this matrix is, of course it has to be square. We're only defining determinants for square matrices. No matter how big it is, we can define we can determine the determinant by what's called cofactor expansion. What we do, remember in the cross product, you took the first row, the ijk. Well, now we have not just 3, but 1, 2, 3, 4 numbers. What we do, same thing as we did before. Take the 1, eliminate the column and the row that that number lives in, and take the determinant that's left. So the determinant that's left is the 1, 1, 1, 2, 3, 2, 1, 1, 2. So our first term is going to be 1 times this matrix. Then we take a minus. So we alternate the plus and the minus. Minus 2 times the determinant of the matrix that's left when you get rid of the column and the row that the 2 is in. So we have 0, 6, 4, 2, 3, 2, 1, 1, 2. Plus 1 times the determinant of the matrix we have left when we eliminate that column and that row, and we get 0, 6, 4, 1, 1, 1, 1, 1, 2. 0, 6, 4, 1, 1, 1, 1, 1, 2. Because we've eliminated the row and the column that that 1 is in. Then minus 3, eliminate the column, the row, and we have left 0, 1, 2, 6, 1, 3, 4, 1, 2. So this is actually a recursive procedure. Now how do we get that? Well, we got to get the determinant of this 3 by 3. So how do we do that? The cofactor expansion, just like the cross product. 1 times whatever's left, so that's this 1, times whatever's left after you eliminate this column and this row, 3, 1, 2, 2. Minus 2, that's this 2, times the determinant of whatever is left after you get rid of this and this. 1, 1, 1, 2. Then it's this number, 1, times whatever's left when you get rid of that column and that row. 1, 1, 3, 2. Okay, then we go on to the next one. This matrix, we got to get the determinant of this matrix. So we've got to break it down into 0 times the determinant of 3, 2, 1, 2, minus 2 times the determinant of 6, 4, 1, 2, plus 1 times the determinant of 6, 4, 3, 2. Then we've got to break this down. Okay, I'm getting tired, but I bet you see the pattern. 0 times the determinant of 1, 1, 1, 2, minus 1 times the determinant of 6, 4, 1, 2, plus 1 times the determinant of 6, 4, 1, 1, minus 3, then we got to write out the determinant for this. And then once we break it down, once we keep to, we have to, if we have a 5 by 5, then we break it down to 4 by 4s, 3 by 3s, 2 by 2s. Once you get down to the 2 by 2s, then you can get the determinant of this. 1 times 2 is 2, minus 1 is 1. What did I just say? Oh, we're up here. This is the first, this is this first matrix. Okay, so 3 times 2 is 6, 2 times 1 is 2, 6 minus 2 is 4. 1 times 2 is 2, minus 1 is 1. Oh, sorry. So minus 2 times 1. Then 1 times 2 times 1 is 2, minus 3 is negative 1. Okay, and then we have 4 minus 2 minus 1. That's 1 times 1 is 1. And you can see it's arithmetic intensive, just like everything in linear algebra, it seems. It's computationally intensive, but we finally get a non-zero determinant. So what does that tell us? We know that this has an inverse, but we're getting there. Wait a minute. So this is how this is traditionally the way that determinants of n by n matrices are defined, with this cofactor expansion. So let me put exactly how we write out the cofactor expansion. So we have an n by n matrix, a square n by n matrix. To determine the determinant, we take the ith row. It turns out you can take any row. It doesn't have to be the first row. It can be any row. And so if you take the entry in the ith row, the first column, then you're going to eliminate that row in that column, and Ci1 represents the matrix you get when you eliminate row I and column 1. And the only problem is, to account for the alteration in sign, SIGN, we've got to say, well, this cofactor is equal to -1 to the I plus j times the determinant of whatever you're left here. So, okay, let's do an example. Let's do an example. Problem 11 on page 267. He gives you, here's the matrix, the usual 2 by 2 matrix. And he says, write out the cofactor matrix. Okay, these are the cofactors, right? Right here, these are the cofactors. And notice there is a cofactor for each I and j. That cofactor is the determinant of the matrix that you're left when you eliminate row I and column j, times -1 to the I plus j. So C11 would be what we get when we eliminate the first row, first column. Well, all we have is D. -1 to 1 plus 1 is -1 squared, that's 1, so it's just D. C12 would be what we're left after we take away the first row and the second column. And that would be C. That's all we have left. But first row, second column, 1 plus 2 is 3. -1 to the 3 is a negative. So this would have to be a negative. C21 is what we're left with when we eliminate the second row, first column, so it's just, second row, first column, so it's just B. But notice 2 plus 1 is 3, so -1 to the 3 is -1, so it's negative B. So we get this what he calls a cofactor matrix. Now, one more example. This is problem 11, page 261, continued. He says, here's the matrix B. Find its determinant. Well, this one is easy because we've got a row that has 2 zeros, only one non-zero element. Oh, that's good. So we can use this row to build the cofactor expansion. So I'm going to do 7 times the matrix left when I take away the row in the column that 7 is in, 2, 3, 5, 6, minus 0 times what I get left when I take away that row in that column, plus 0 times what I get when I take away that row in that column, 1, 2, 4, 5. Well, it doesn't matter what these are 0. So all we have left is 7, and then it's 2 times 6 is 12, minus 3 times 5 is 15, -3 times 7 is -21. If we wanted to write out every one of the cofactors, he asks you to write out every one of the cofactors. So D11, what do you have left when you take the first row and first column out? You have 5, 6, 0, 0. Its determinant is 0. Okay, D12, if we take out the first row, the second column, we have 4760. So the and -1 to the 2 plus 1, which is 3, -1 to the third is -1. So we'd have 4 times 0 is 0, minus 6 times 7 is 42. So minus a minus 42 is 42, and so forth. I didn't write them all out. Part of your homework is to finish that. So, okay, all we've done, I've just shown you how to calculate the determinant based on cofactor expansion. And small children would point and laugh at you if you didn't know what cofactors were. So that's important. Where do determinants come from? Well, actually, you can show that they're important because of our process, our good old process, we always come back to this, of elimination. So remember, when we do our usual Gaussian elimination, the first step we want is to zero out this entry right here. So the way we can do that is we can, even though we have variables here and not numbers, we can take -c times row 1 and add it to a times row 2. Well, if we do that, then in this entry we're going to get -ca plus ac. Good, that'll be 0. Here we're going to get -cb plus ad. Haha. Okay, so based on all the elimination work we've done, the Gaussian elimination work we've done, if this entry, this pivot is 0, what happens? Well, if our right-hand side, our b, is actually a value like 1 or 2, we have no solution. If it's a 0, then we're going to have an infinite number of solutions. Either way, we don't have one unique solution. Therefore, we have no inverse. We can't get an inverse matrix. So that's why the determinant is important. If we know this determinant, we know whether we can get an inverse or not. And it just comes from the fact that every time we calculate a determinant, we're really calculating this last entry, this last pivot. Okay, so let's be brave. We did a 2 by 2. Let's do a 3 by 3. And you can see how complicated it gets, how quickly. So here's a 3 by 3. First row, second row, third row, first column, second column, third column. Okay. So we want to do our usual elimination. So I'm going to do something like I did with the 2 by 2 matrix. To get rid of this, I'm going to multiply this row by -a21 and multiply this row by a11 and then add them. And I get that. And I get that. Of course, the first row stays the same. Then I want to eliminate this entry. So again, I'm going to take a32 times this row and subtract a11 times this row, and I'm going to get this. I think I said that right. Not sure. I'm going to multiply a11 times this row. Let's say a11 times this row, and negative a31 times this row, and add them. I said that right that time. So we get this. It's a little tedious. It's algebra. Okay, now we want to zero out this one. Oh my God. So we've got to take, let's say, this times the negative of this times that, plus that times this. Ooh. Wow. And that is, then we zero out this one, and we're left with, trust me, but you can, if you want to, you can dig it out and check it. We're left with this expression here, that's this delta, that's the determinant. If that's 0, then we have either no solution or an infinite number of solutions, but we don't have a unique solution, so the matrix doesn't have an inverse. So look at this. We have 1, 2, 3, 4, 5, 6 terms. You might recall that. Notice that, well, wait a minute, let me say this. We have 6 terms. Notice that A11 is here and A11 is here. And if we factor out the A11 from these two, we would wind up with A22, A33 minus A23, A32. So that's as if we're taking the cofactor expansion using this first row. Notice we also get A12 here and A12 here. And if we factored out an A12, we would have A23, A31 minus A21, A33. This is where the cofactor expansion comes from. So, obviously, if we had a 4x4, it's going to get really tedious. But at least you can see that this is where this comes from. It has to do with that last pivot. Okay. Let's get back to the real world and say, how do programs like MATLAB and Maple and Mathematica and any Fortran thing, any Fortran program, how do they actually find determinants? They don't do it with cofactor expansion. They don't do it with Strang describes the long formula, which looks like this, where it's just a string of products, but it can be rewritten as a cofactor expansion. Computers, you don't program it that way, it's too labor intensive. The way they program it, we got to go back to LU factorizations. So I highly recommend that you review LU factorization. When we do our LU factorization, remember, using elimination, we get our L matrix with ones along the diagonal, and our U matrix with upper triangular, U meaning upper triangular. Okay, so notice what the determinant of this matrix is. If we do our cofactor expansion across this first row, all we're going to have, these are 0 times whatever, 0 times whatever, so the only contributing term is going to be 1 times this matrix in here, because we're going to eliminate this and eliminate this, right? So it's going to be 1 times this matrix in here, which, because it has a 0 up here, it's going to be 1 times 1 minus 2. Well, that amounts to 1 times 1 times 1. Whenever you have a diagonal matrix, or lower triangular, upper triangular, or diagonal, the determinant, because of the way the cofactor expansion goes, is just going to be the product of the diagonal elements. Yay, that's easy. So the product of these diagonal elements is 1. The product of these diagonal elements is negative 12. So what's the determinant of this original matrix? Negative 12. Why? Because the determinant of L is 1. The determinant of U is negative 12. The determinant of A is going to be the determinant of L times the determinant of U. Now he proves this for 2 by 2 matrices, but he stays away from n by n matrices. And only because it's labor intensive to show this. But this is actually how programmers do it, how it's programmed. With an LU factorization, and then all you have to do is take the product of the diagonals in the U matrix. One problem. If you remember, you can't, sometimes in order to get the LU factorization, you have to exchange rows. So the only problem is, if you exchange rows, you've got to multiply by negative 1 raised to the power of the number of row exchanges. And in some of the exercises you do, you'll see why that's true. Because remember, to do a row exchange, you multiply this by a permutation matrix. And then you can see that the permutation matrix, if there's an even number of row exchanges, the determinant of the permutation matrix is going to be 1. If there's an odd number of row exchanges, the determinant of the permutation matrix is going to be negative 1. And that's where this comes from. Okay, so let's talk about some other properties of matrices. The determinant of an identity matrix is 1. We already know that because we know if it's upper triangular, lower triangular, or diagonal, you just take the product of the diagonals, and the product of the diagonals for an identity is 1. We already mentioned that row exchanges change the SIGN of the matrix, of the determinant, by negative 1. So if you have one row exchange, you got to multiply by negative 1. If you have 2, it's by 1. If you have 3, it's by negative 1. There are a few other properties that he mentions. He uses specifically 2 by 2 matrices, but you can't prove all this for n by n matrices. And maybe we'll look at that next week. So if you have a matrix like some number, it's a 2 by 2 matrix, A, B, C, D, but you have the top row multiplied by something. Well, then it's just going to be T times A, B, C, D. And you can just get that matrix, get this determinant, TAD minus TBC, factor out a T, and you can see that it's T times AD minus BC. What's also nice, if you take one row and add it to another row, or even to a multiple of the other row, you don't change the determinant. If you add some number to a row, if you add numbers to each element of a row, then you'll find that the determinant of this matrix is the same as the determinant of ABCD plus the determinant of EFCD. So these are just some properties of determinants. Okay, so we've covered a lot. If you want it way long-winded, you can watch Strang. Otherwise, what I'm going to do is assign some homework problems that will be due Monday, but I'll collect them along with the other homework problems, but I'm not going to give you something to do right away and send to me. So check that out on Moodle. The assignment will be on Moodle. And I will see you Monday. My daughter-in-law, thanks for your patience. My daughter-in-law is doing well, except she's tired. But the surgery went perfectly. Everything's fine now. She just needs to heal up a little bit. But all is well. My granddaughter is gorgeous and eats a lot. Doesn't sleep a lot, but eats a lot. And she's getting big and strong. So I will see you Monday for sure. Bye.